Dr. Simhachala Rao Chikkala is an engineer at the U.R. Rao Satellite Center, URSC, Indian Space Research Organization. He's a PhD from IIT Kharagpur, where he researched boiling in microchannels. His expertise includes subcooled flow boiling, microchannel heat transfer, and thermal systems optimization for space applications. His key publications cover bubble flow in microchannel heat sinks, miniature heat pipes for the spacecraft electronics, and multiphase flow systems, as well as the space radiator optimization to the mechanical control loops. Dr. Chikkala sir will speak on two-phase heat transport devices for the electronic thermal management. Requesting Dr. Simhachala Rao Chikkala to begin the session.
I'm audible. Yes. So, thank you very much for inviting me for this lecture. Especially for the and I'm going to speak on phase change heat transfer for thermal management of electronics. Though I am managing thermal management of electronics, I will be focusing on the spacecraft related thermal control, not on the terrestrial applications, because though the working principle is same, but the complexity of construction and the control is complex. Phase change heat transfer devices. There are so many phase change heat transfer devices. However, main focus is in the spacecraft thermal controller, heat pipes, fluid loops, vapor chambers, etc. Terrestrial applications have several applications like laptop and notebook computers, PCs, MEMS, refrigeration and air conditioning applications. When it comes to spacecraft applications, basically satellite electronics cooling and re-entry vehicle thermal controls. And coming to aircraft applications, it's avionics cooling and anti-icing system like this one. And why thermal management is required is basically every 10-degree raise in electronics reduces slightly off a half. Actually, you can see the Arrhenius equation, right? Even the initial days of our thermal tests on spacecraft, battery person in the power systems group, they used to comment that every 1 degree raise in battery will reduce its life by 1 year. And the environmental impact on electronics is, if you compare to all others, temperature will have the biggest challenge. Is 54% impact on the present thermal technologies we are using in thermal control of electronics in spacecraft are multi-layer insulation, optical solar reflectors, optical paints, thermal grease and all, and diffuser plates, passive radiating coolers, heat pipes, heat pipes, vapor chambers, and heat switches. These are all passive thermal control technologies. And when it comes to active thermal control technologies, thermal coolers, heaters, fans, thermal louvers, cryogenic coolers, and pumps. I will be for another 40 minutes. I will be speaking on heat pipes, various types of heat pipes, and pumped fluid loops. Pumped fluid loops, basically, I am emphasizing more because we are working on last few years. It's an advanced stage of development. Pumped two-phase loops with the microchannel evaporation. Heat pipes are developed very long back because these contributes the significant thermal control for various thermal control technologies in spacecraft, especially DWDs. Because it transport significant heat over a considerable distance with a minimum temperature difference between end to end by using the evaporation and condensation of the working fluid. No active devices are required, and it's a device of high effective thermal conductance, less thermal response time. You can see the famous figure where if you dip a copper water heat pipe and a copper rod in a 80-degree temperature bath, the time required for a copper water heat pipe to reach is roughly 4 seconds. And, a typical aluminum ammonia heat pipe will have 1,000 times conductivity better than a aluminum. That is the conductivity level of this one. However, the complexity of construction is little difficult. Heat pipe selection, basically heat pipe design starts with 3 major parameters like selection of the container material, selection of the working fluid, and selection of the wick structure. These are the major parameters. However, there is a big design process. However, these are the main building blocks for selection of the heat pipes. First, it should have a compatibility of the container should have a compatibility with the working fluid, and it should have high thermal conductivity. It should have ease of fabrication because some of the axially grooved heat pipes should have a extrudable quality. Extrudable quality should be very high, and it should have a less porous. It should have a good wettability. And when it comes to selection of working fluid selection based on the operating temperature range basically, because in spacecraft the operating temperature range is between -40 to +60, whereas in the ground it will be 10 to 80 and all. So in that particular temperature range we have to see figure of merit. Figure of merit is a function of surface tension, latent heat evaporation and inversely proportional to viscosity. This parameter should be very high in the operating temperature range. And also it should have a good compatibility. It should have a good thermal stability and it should have a good thermal conductivity also. And the selection of weak structure should be like should have minimum capillary radius to gain more capillary pumping and high permeability, so less pressure drop, and good wettability and compatibility with the container. There are several weak structures available here. There are, but basically we use axially grooves are considered for special application because what happens is there are other weak structures like composite weak structure or other weak structure which give better performance than the axially grooves, but since the reliability of axially grooves is better because they are directly embedded in a thermal in a container, so there is a less chance of failure. Whereas if the mesh wick or any composite wick, when it flows on the spacecraft, there is a chance that after 10 years and all they may come out of the container. These two are the two types we are using here. These two are the two types of heaters which currently we are using. Actually, groove heaters with a groove structure with a trapezoidal grooves and single core heat pipes. Of course, we are using a miniature heat pipe, miniature axially grooved heat pipes, and we are using ammonia as the working present application. These are the applications. The first row consists of the heat pipes which are using for the spacecraft thermal control. These are the configurations. We will be using several bend types with a dual core, single core, and this is the far right will show the actual panel with the embedded heat pipes in a honeycomb structure, and all the payloads we can see the payload. This is the typical panel structure of a spacecraft. Okay. This is the spacecraft panel. Okay. When it comes to terrestrial applications, copper water heat pipes can be rigorously used for various applications. There are several types of heat pipes which I am majorly focusing on constant conductance heat pipes, variable conductance, and capillary pump loop and loop heat pipes, micro miniature heat pipes, and flat heat pipes or vapor chambers. So far, what we have done is a constant conductance heat pipe is actually a closed device which will have a constant some stage of working fluid, and when it comes to variable conductance heat pipes, variable conductance will have what will have to do. We will introduce one reservoir at the edge of the condenser. Why we will do this? Because there are applications in spacecraft where we have to have a tight temperature control, especially like atomic clocks, and in some of the low planetary missions, we should have a very tight temperature control like plus or minus 0.2 to 0.5. In such applications, we cannot use a constant conductance heat pipe. So though the sizes or weight is more, variable conductance heat pipe is more prominent for some of the applications like atomic clocks and all. So what it will do is, though the temperature, when the heat load increases for more, what happens is will increase the condenser area by this pressure. It will it will increase the condenser area so that the temperature will not go up. And whenever there is the not requirement of when the heat load is zero, when it is not operating, what happens is it will reduce the condenser area, and thereby it will increase the temperature. So you can see that for a constant conductance heat pipes, that delta T will be increasing linearly with Q. Q by delta T is always constant, whereas for a variable conductance it's almost uniform. Of course, at very high heat loads it slightly increases, but it is almost nearly isothermal. It will maintain in spite of increasing the heat. However, it will add a weight because weight is a more constraint. So it will add weight. However, since considering the application point of view, we have to use variable conductance. Loop heat pipe. Actually, loop heat pipe. What happens is there are applications where we cannot handle with the heat pipe. There are some applications where some of the payloads are very high heat dissipating, which we cannot meet with the regular heat pipes because of some limitations like capillary limit. Basically, so what happens is when the height loads are high, we have to have a one rugged system. Here, there it will leads to loop heat pipe. Loop heat pipe, what it is, the evaporation and condensation will happen in different zones and interlinked by smooth wall tubes. Evaporator and basically the evaporator will have a primary wick, basically for vapor generation and capillary pumping, and there is a secondary wick at in the middle where it will keep liquid flow from condenser. Actually, this is the evaporator zone and this is the condenser zone. Once heat is applied, the vapor travel to the condenser zone, and by releasing latent heat of vaporization, the subcooled liquid come back to the evaporator via a compression chamber. This compression chamber will have enough liquid to supply the depletion of liquid at any stage, and also this there will have a one rod where the liquid can be pumped from the CC to the evaporator. Basically, the key components are evaporator, condenser, flow transport lines, and LHP transport heat from spaceport bus to deployable thermal radiator. We can increase the radiator area by a foldable, and whenever required, we can deploy it and use as a more area. Key specifications are 500 watts. Whatever we have developed so far is a 500 watt ammonia loop heat pipe with a porous nickel because the nickel we have used, and operating temperature between -10 80. And this is the picture of the mini loop heat pipe developed at URSC with flat plate evaporator. And this is the picture showing how we link the source panel where all the evaporator components will be here, and the radiator will be connected with a condenser zone, and there will be a flexible link here between the evaporator to the condenser. There is a difference between, there are two types. One is capillary pumped loop and loop heat pipe. Basically, the position of the compression chamber differs in both the places. In the capillary pumped loop, the working principle is same. However, the reservoir position will be at far from the evaporator zone. However, the compression chamber and loop heat pipe is in line with the evaporator. There is no much difference between capillary pumped loop and loop heat pipe because various agencies will use capillary pumped loops or loop heat pipe than this one. However, there are very minute difference because there are, if you see, both can handle high heat flux heat loads, both can have a good temperature control. However, both having a startup issues because what happens is there is a lot of resistance between at the heat input zone to the where it has to start boiling. So for that there is a startup issues, and there are instabilities in capillary pumped loop. There are no instabilities in loop heat pipe. Why? Because of the reservoir configuration. Because if any heat leaks from the evaporator to the compression can be arrested in loop heat pipe, but it is slightly difficult in capillary pumped loop. However, both are almost performances similar. Micro heat pipes. Actually, micro heat pipes are there are some applications where some of the small diodes, CCD, charge coupled devices in spacecraft will have a small heat load, but it will have a high heat flux, and which cannot be reachable with a normal heat pipe. So what we'll do, we have to use a micro heat pipe. So what it will have is micro heat pipe is a device which will not have a circle cross, it will have either rectangular cross section, because the sharp corners will act as a capillary structure. There is no separate big structure. Sharp grooves will act as the capillary pump. Basically, there is a hydraulic radius. Hydraulic radius should be if the capillary radius is greater than 1, it will be considered as a micro heat pipe. basically laser diodes, photovoltaic cells, and welded electronics. The heat load capability will be roughly less than 5 watts, not more than 5 watts of heat load. And the length of the heat pipe is around less than 50 mm. There are flat plate heat pipes or vapor chambers. Actually, these are hollow chambers filled with screen mesh or sintered wick or any auxiliary glues, which acts as a capillary structure and filled with a two-phase fluid. It can be circular or rectangular, any square shape. Unlike heat pipe, which transport from heat from one end to other, what a vapor chamber do is it absorbs heat from a small area and spread across the large area. Basically, what it will do is it will reduce the high heat flux device to a low heat flux device. It's a flux transformer. Basically, because presently we are using some of the diffuser plate, aluminum solid plates in the between the heat pipe panel to the electronics components. So we are planning to replace these diffuser plates with flat plate, because it will have a high heat flux compared to the heat pipe. And the present configuration which we are developed is roughly 50 watts and working fluid is acetone, and 3 mm is the thickness of the plate, 150 mm. The operating temperature is roughly minus 42 plus 90 degrees. Yeah, heat switches. Heat switches are actually there will be basically there are applications where actually some of the times there will be parasitic loads. Sometimes heat will be on, sometimes heat will be off. But what happens is when we use regular thermal control devices, the heat transport will be happening. So because of that, when the system is off, what happens is it is getting reduced because of heat pipe is transferring the heat to the radiator plate. So because of that, to operate it in the operating temperature range, we have to add some heat. This will add weight, like some of the input heat power has to be added to the to control it the required operating temperature. These devices, for that we have to add heaters. So to avoid these heaters, because even a 1 watt heater will give some 15 kg of battery size in some of the lunar missions and some of the interplanetary missions. So to avoid that additional mass, there is a concept called heat switches. Heat switches, what they will do, they are devices which acts as a good thermal conductor or good thermal insulators. Means whenever required, it will have as a it will act as a condenser. It will act as a good thermal conductor, and whenever it is not required, it will act as a good thermal insulator. If you can see, there is it will switch their action by changing the thermal resistance between source and sink. You can see here. This is actually some of the package where it is when it is cooled, the heat switch will be the gap will maintain, and it will be a low conducting flexible rod. So what happens is the connection will be switched off between these two. Whenever there is a hot, what will do is it will join both two together, and the conduction pass will take place, and we can use it. It can transfer the heat to the radiator. So with this, you can optimize the radiator area and reduce the size of the package. So there are two types of heat switches. One is in the passive kind, and the other is in the active kind. Basically, however, we will be preferring the passive kind, like differential thermal switches and all. And the main advantages are efficient thermal management of space package with cyclic operation, and the reduction in parasitic heat loads and payload detectors from the cooling systems. This is a typical heat switch. Of course, this development is under progress. It's not yet realized. We are in the planning of development. So coming to two-phase mechanical pump tubes, this is the device which we are recently developed, and it is in the advanced stage of development. Actually, two-phase MPFL is a device which can transport large heat loads or heat fluxes from evaporator to the condenser using a centrifugal pump or any gear pump. Of course, it will happen with the working fluid, but the boiling is happening at the evaporator zone. There are this is the evaporator where the heat dissipation is happening, and once the heat, because of the heat load, the fluid converts to vapor and travel to the condenser zone, and releasing the heat of evaporation, and with the subcooled liquid comes back to the pump via a pump, and there is a device called accumulator. And this accumulator, what it will do is it will nullify the pressure fluctuations due to the high heat loads. Actually, whenever there is a high heat load, the pressure of the system will increase. So what it will do, it will extract that pressure and pump the liquid at the required pressure. These are the components: magnetic drive pump, drive electronics. Drive electronics are required to pump the drive the pump, accumulator, pressure sensor, mass flow meter, evaporator, and condenser and plumb lines. Advantages of two-phase MPFL over the traditional thermal control technologies: it will handle high heat fluxes or high heat loads, ability to accept and reject at multiple locations, like unlike loop heat pipe, because in loop heat pipe there is a limitation on the construction of the evaporators, because evaporator construction is very complex in loop heat pipe, whereas here a microchannel evaporator can be easily fabricated. Flexibility, integration, ground level test. Heat pipes testing at the ground level is very difficult because adverse tilt and all, it will not function. Here there is a pump, we can test at different ground level tests. And adaptability of late changes in spacecraft design. Once any other device, once it is fixed, design is fixed, once everything is fabricated, everything is constructed, we don't have an option to change the design. But here we can change the design, we can change the pump flow rate, and we can modify accordingly. And transport heat loads across the very longer lengths. There is a coming to passive heat transport devices, there is a limitation on the length of the heat pipe or loop heat pipe, whereas for this we can have a very longer length based on the pump capacity. You can see there is I have made a table where the maximum heat transport capability of whenever there is a 10 kilowatt, more than 10 kilowatt missions, spacecraft missions, we cannot use a loop heat pipe or this one, we have to use pump fluid. Heat flux is up to 100 watt per centimeter. However, the temperature difference delta T we can maintain. Length of the transport will be very high. Ease of integration is excellent. Flexibility is good. Sensitivity to gravity is very low because rest of the heat pipes and loop heat pipes have there is a high sensitivity towards the gravity. And multiple evaporators, we can use a multiple evaporators, means all the packages can be linked through a pipe, microchannel evaporators, and we can transport the link. And adaptable to late temperature control or remotely located packages, it can handle very nicely. These are the differences of the advantage of MPFL over the.
Can I just ask one question? So to put it in perspective, what would be the watts of your pump?
How many?
How many watts would your pump need?
Pump need, yeah, it is based on the pump capacity.
For this 2 kilowatts, how much are you?
How much? Roughly, we got 16 grams per second. 16 gram per second.
Okay.
It is again depends on single phase or two phase. If it is a single phase pump loop, it will be very high. If it is a two phase, it is less. So two phase pump fluid will require very less flow rates, and it will have a good uniformity, temperature uniformity. However, in single phase, we will have a high flow rates. It is 16 grams per second pump which you have used.
That's fine.
I just to give a flight heritage of these pumped fluid loops. Significantly, most of the missions they have used a single phase pumped loop. You can see the wattages like 14 kilowatt, 14 kilowatt, 14 kilowatt, and all 6 kilowatt and all. People have used a pumped fluid loop because with the heat pipes we cannot meet that requirement. And there are two phase pumped fluids also flown with TLC linear spacecraft and all, with roughly 1.5 kilowatt, 4 kilowatt. Presently, we have developed a system with the 1 kilowatt pumped fluid loop, and we are augmenting it up to 4 kilowatt pumped fluid loop. This is the device which we have fabricated and tested and realized. We have done up to 1 kilowatt testing, and the pump we have used is a air pump, and working fluid we have used is acetone and pentane, because our operating temperature is between -22 plus 80, and the evaporator is a microchannel based evaporator we have used. Why? Because microchannel evaporator will have a high heat flux density, high heat transfer coefficient, and high temperature uniformity compared to a normal tubing. And the mass flow meter we have used Coriolis mass flow meter, and sink is the cryostat. Actually, you can see we have used multiple evaporators here. These are 4 evaporators we have connected in parallel, and the pump will be supplying the liquid to these 4 evaporators, and the vapor is traveling to the heat exchanger like a condenser, shell and tube heat exchanger, and then the fluid is coming back to the evaporator via a pump and an accumulator. Here we have used a gravity based accumulator. However, for the spacecraft we will be using a two-phase accumulator. And we have done several tests on this, and we have got a good results. This is the insulated, right side gives the insulated. This is the result for the evaporated temperature. If you see the average evaporated temperature roughly is at 1 kilowatt, we are obtaining up to 65 degrees. This is what we have. We desire. That is the operating temperature, and we could able to achieve this one. And the delta T between both will be around 15 to 20 degrees. And the right side picture shows the comparison between numerical and experimental, and we got a very good agreement between both. I just share one video of our plots actually. When there is when we are giving 100 watts, 200 watts, 300 watts, 400 watts, 500 watts, and 600 watts, 800 watts, and there is a dip in the temperature where there is a onset of nucleate boiling. Once there is a boiling initiation, there is a fall in the temperature, and then there is a uniformity of the temperature. So this clears the difference between the single phase and there is a two phase zone. And these are all 4 evaporators, and this is the condensate temperature. Green one is the condensate temperature, rest of above evaporated temperature. This is my last slide. I want to show how various devices will be used in a spacecraft panel. Let's see. These are the heat pipes embedded in a panel. This black color will be the panel, spacecraft panel, where we will be embedding the heat pipes. On above that, there are packages. These are the packages of the spacecraft, which will be transporting from where the heat load is being transferred to the radiator plate down. Actually, the heat pipes will be connected in a crisscross network. Top will be called as a header heat pipes, and bottom will be outer heat pipes. So from bottom to top, top to bottom, heat will be transferred to the space. And there are vapor chambers between packages to the panel. Vapor chambers will be connected to reduce the high heat flux to the low heat flux. And these are straps, thermal straps. Thermal straps are used as a flexible linker. Whenever there is a remotely located packages, to link from the package to the radiator, we will be using thermal strap because there is no provision to link the heat pipe. And this is the loop heat pipe. You can see the compression chamber of loop heat pipe here. Means this is the entire system is an evaporator system, and then the fluid means the vapor will be coming to the this radiator zone, and the subcooled liquid will pump it back to the again to the evaporator system is heating zone or the heat dissipating zone via a compression chamber in LHV. And this when we are using MPFL, that will be replaced with an accumulator, and in an MPFL the pump will be used for an MPFL. So again the liquid again converts to the vapor, and this cycle will continue, and large heat transport can happen between the evaporator and the condenser. So this is my conclusion.
Thank you, Dr. Simhachala Rao Chikkala, for your informative session.
We'll ask some questions.
Yeah.
We'll take some questions. So, your experimental setup, that is 1:1 scale.
No, it is a means you are telling real application.
Yeah.
No, not yet. It is a ground level test we have done, because what happens is we have arranged multiple. Actually, of course, the evaporator is 1:1 scale, but the arrangement is not same. Not same, because what happens is we have arranged evaporators in a uniform fashion in a parallel fashion, but whereas in a spacecraft, package will be in a haphazard manner it will be placed. So we have to link. We should link in a plumbing will be little challenging. Okay, so it is not 1:1 as well.
But roughly, what would be the dimension in physical dimension
of
this evaporator?
Evaporators again, the evaporators sizing will be different because based on dissipation. What we have used is a 50 mm length, 0.5 mm. It's a 500 micron by 500 micron. 0.5 mm by 0.5 micro channel we have used, and some 40 micro channels, and roughly 50 mm is the length of the micro channel block. So yes, we have assumed some like each evaporator can handle roughly 250 watts. So similar similar heat load dissipating packages that we can use same evaporator. But if the package is dissipating 400 watts, then we have to use some, it's little different. Like we have to increase the grooves, means the channel optimization we have to do. Like number of grooves we have to increase, and we have to increase the dissipation, accordingly dissipation we have to increase. But this is for a lab model. It is not yet flown model. Yeah, please.
I have two short questions.
Yes.
First one is related to your second last figure where you increase the heat flow and then temperature is rising.
Which one? Yeah, yes.
This was for the heat pipe system or for
No,
the
sir.
pumped?
Pumped fluid loop. Pumped fluid loop.
Because when you say that's onset of boiling, the delta T between condenser and evaporator is increasing. I would have thought as soon as you come into the boiling regime that the thermal resistance is decreasing,
Yes.
and so the delta T should decrease, but it's just the opposite.
You're talking about the delta T between evaporator and the condenser?
Between
Or-
evaporator and condenser.
Yeah. Yes. Yeah. No.
The green line is the condenser.
Condenser. Yeah. Yes. No. Actually, the delta T at the I'm talking about delta T at the evaporator is uniform.
Okay.
Delta T among the if you see the single phase MPF, single phase zone, the delta T at the evaporator is slightly higher.
Okay.
And once the two phase boiling starts, the evaporator is at the uniform temperature. But the delta T between evaporator and condenser will be slightly higher because condenser will be at the subcooled zone. Means it will be transport, means it will be separate zone.
Okay.
Where it is releasing latent heat of evaporation and coming back as a subcooled liquid. The subcooled liquid will be always at around 40 degrees something around, and whereas our evaporator is roughly around 60 degrees. So the delta T will be almost similar between evaporator and condenser. If it is a closed device like a heat pipe, yes, the delta T will be between evaporator and condenser will be less. But since this is both are separate, the delta T will be slightly higher.
Maybe a second very short question. You didn't talk about pulsating heat pipes.
Pulsating heat pipe.
Pulsating heat
Yeah,
pipes.
pulsating.
That's something that finds its way into space.
So far, we have not seen the application of pulsating heat pipe because pulsating heat pipe has some disadvantage like delta T is high. Though the construction is simple, but the delta T is significant, was comparatively high compared to axially grooved heat pipe. And also, we have to have a network. See, in a panel, in a spacecraft panel, we have to isothermalize the panel. So for that, heat pipe network, normal constant condensed heat pipe network is very comfortable. Whereas pulsating heat pipe, making a heat pipe network with a big network with this repeated vapor and liquid slug flow and vapor flow will be very difficult to design. Though for small applications, yes, we can use it. But as a spacecraft application, we are seeing little escape.
Question maybe directly to this graph. Why are condensers warmer in the low temperature range?
Low temperature range means at here, right?
Exactly, the condenser is warmer.
Yeah, and it's a single phase because condenser is at connected to a chiller at -40. If you see, we are fixing at -40. Okay.
Yes.
So when it is at -40, chiller is -40, condenser is roughly around -20 or something. -20, -30 around. Okay. So once we give 100 watt heat load, it will slightly increase. See, it will be at -20 or around that temperature. Once we raise the temperature, once we increase the heat load, then only the condenser temperature will come up.
But why it's higher than the evaporator? So if you heat in the evaporator
Yeah.
and you cool in the condenser.
Yes, yeah, because initially this is at I think there is a small difference. No, this is the evaporator temperature and this is the condenser temperature. Because actually what happens is initially before giving, when it comes to ambient, so okay, -20. Initially, almost they are at the same temperature. They are not much different, but there is a slight delta T between the evaporator and the condenser. Actually,
That's probably.
yeah, please go ahead.
Can you say something about whether you get instabilities in your microchannels when you go to higher heat flux?
Yes,
What
yes,
happens?
yeah. We have encountered instabilities. Basically, when we initially used a straight channel rectangular microchannels or square microchannels. What happens is we at the around the 600 watts or 800 watts roughly. What happens is the flow has been reversed. Flow reversal is happening because of the repeated elongation of the bubbles. So what we have done is we have cut the microchannels to zigzag cross section. So we have arrested those instabilities and we could achieve up to 1 kilowatt. We have changed the cross section from rectangular straight to zigzag channels.
So what limits the maximum heat flux that you can get?
Roughly with the present configuration, we could get up to 20 watt per centimeter square. But still, we have to do tests going on, so we can increase the heat flux based on configuration.
In the same direction.
Yeah, I'm coming.
Okay, so in the same direction, I have a question. So you also mentioned that you put the wick, right, in the surface of the pipe, and there's also you can use the triangular cross section with access natural wick. So don't you expect that bubble might trap there in the wicks because heat is coming from the side? Whatever liquid enters, when it evaporates, then bubble will trap and it will create this.
There is a boiling limit. So we should not. If you see for a heat pipe, there are several limits like boiling limit, sonic limit, and bottom one is a capillary limit. So we have to restrict the heat load up to capillary limit. We cannot increase up to, and the boiling limit is much higher. So that's what heat pipe has a limitation. Because once it is trap or any hot spots will happen.
Yeah.
So it will not transport the heat load. That is the limitation. So the lowest one is the capillary limit. So like 250 watts capillary limit. So capillary limit will restrict. That is the maximum heat load. We should not go more.
So you expect that in the weak region, it is all liquid, and there might be some bubble formation in between the core of the
Yes.
or core of the heat pipe.
Yes. There can be bubbles, but what happens is that is through radial heat flux. That's what there is a boiling limit. So boiling limit we should not use if there is a hot spots are happening. If the dry out is happening because of the bubbles, we should not heat that much. It's actually what we charge is both liquid and vapor. It will charge. So the vapor will be increasing and liquid will be moving. So of course in the liquid zone, if there is any bubbles are happening, that is a boiling limit. So that you have to avoid it.
So I also had a question to this triangular capillary driven
Yeah.
heat pipe. And it seems that it might be, so the capillary drive will be dependent on maybe the roundness of the corner.
Sharpness of the corner.
Exactly.
Yeah.
So a real world corner might be a little different than a.
Yes.
And, have you looked at that? And the other question is then, I mean, if you're driving it with capillary, you might actually have to want more. We might want more corners, so you would have like a grooved.
Yes.
So do you do this or not?
We have done with a small square cross section with sharp corners.
Yeah.
And we have used even a omega groove at the sharp. We have inserted one omega groove also, and we have tested up to some 5 watts, 10 watts. It is able to transfer.
Because in the end, the transport flux will determine the overall
Yes.
capacity.
Yes. Heat flux is the main this one actually.
How are you planning to get the liquid vapor certification in space?
Liquid vapor
Certification accumulated.
accumulated.
Right now is depending upon gravity.
Yes.
Certification in space, how will you do that?
Space, what we'll do, we will have a meshing. There is a capillary. We will use a capillary wick structure in the accumulator. What happens is, though the whatever the liquid is coming uniformly, it is circulating through the wick and going to the transport region, evaporator region. Okay, so we have to introduce a capillary wick structure.
Have you tested it?
Not yet tested. It is yet to design. Two-phase accumulator is under the design process.
How big are your microchannels? Like
It's a 0.5 mm by 0.5 mm square cross section. 500 microns by 500 microns.
One more question to your interesting heat pipe with non-condensable gas chamber.
Yes.
In the graphs you showed that the heat pipe with a, let's say, non-condensable gas chamber has a more stable temperature profile of the heat flux.
Yeah.
But from the graph it seems to me that the heat resistance was lower. But shouldn't it be the case that if you have two identical heat pipes, one with a non-condensable gas chamber and one without, that the heat resistance of the one with a non-condensable gas should be on the higher limit of the one without?
Yeah, no. Actually, what happens is the conductance factor will be always in a regular heat pipe. The conductance will be constant. Whereas in a variable conductance heat pipe, the resistance will be almost constant.
I mean from the level of the, let's say, heat resistance or from temperature difference.
Temperature
So the
difference.
temperature difference of the one with non-condensable gas should be higher than the one of the...
No. The temperature difference will be lower in a variable conductance heat pipe. The delta T will be lower because it is controlling the evaporated temperature by increasing the condenser area.
So, I mean the temperature difference between
End-to-end temperature difference.
lower with non-condensable gas.
No, not at the non-condensable gas, at the condenser zone. Evaporated to the condenser.
Yeah.
The delta T between the evaporator and the condenser, not at the condensable gas.
Yeah.
Also, in currently some of your missions, like Chandrayaan, like which of these passive or active devices is mostly used?
We have used heat pipes and EGS thermal straps we have used.
Okay.
Rigorously we have used thermal straps to link this. However, variable conductance heat pipe we could not use. We are planning, but we could not use.
So the MPFL is still under
Testing. Means tests are over. Now we are qualification process is under progress because the form qualification, how it runs in the space, vibration test, thermo vacuum test, and all we have to do. So the qualification tests are under progress.
Are there any other questions from the participants? If not, let us thank the speaker. Very nice.
Thank you, Dr. Simhachala Rao Chikkala, for your informative session. I request Professor Arvind Pattabhatt to present the meeting.
Maybe you can do that. Yeah, of course.
It's your turn.
No, I've done enough.
You have done enough.
Sir.
Hold.